I'm Sean from ARM in Cambridge. Thank you for joining me today. I'm going to start by explaining what I'm talking about and see if I can share my screen. So this format of online presentation is new to me, so I hope it all works. I'm going to talk mostly about the types of work that I've been doing over the past 25 years, using ARM as an example rather than talking about ARM in too much specific detail. And I'm going to try to avoid getting too technical, but it might be hard to get the right balance of using some technical jargon and getting the detail right. So if there are things that I'm talking about that don't make sense, just ask in the chat and I will try and go over it in a little bit more detail to explain it. So I'll start by talking about my career in general, what I did to get where I am now. I started with a radio design consultancy, did a little bit of work with telecoms infrastructure, and then I switched from analog electronics to digital electronics at ARM. I need to talk a little bit about ARM's business, the way that they make money, which is what we call a business model, and a little bit about how much the technology has changed over a 15-year time span, because that's quite important to explain why there are still interesting things to do in a field that's probably about 50 years old. I'll talk about what I do specifically, the types of projects that I work on, the features in the products, and how the teams work. I'll cover kind of the design and the test aspect of it, because those are both very important and attract different people. And I'll touch on the other technical careers that we have in ARM. Obviously, it's a big company. There are lots of non-technical jobs in ARM, but I'm not really going to talk about that today. In terms of the questions, if you ask questions as we go along, I will try and keep an eye on what's going on and answer things when I get to a suitable point with what I'm talking about. So to start with, I was in the first year of taking GCSE exams. Seems quite a long time ago now. I did the kind of default A-levels for engineering, which is 2 maths and further maths, physics, and I chose chemistry as the other science. The school had an amateur radio station and a radio club, and I was that was one of the things that I was involved in, kind of extracurricular, and pushed me in the direction that I started my career with. But it was kind of a fortuitous connection. The work placement that I did was with a local cable TV company. And at the time, there really didn't seem to be many electrical engineering opportunities available. At university, I did a physics degree. I did apply for some electronic engineering courses, but there was a combination of the specific university and the courses that they were offering. Physics seemed like something that would be interesting in a more general sense, and it didn't seem that the detail of the electronics was that critical to cover at a degree level. So I did a nuclear physics option, and it was, for me, I found it really hard. Interesting, but some of it was really hard to understand. And if you can't understand it, then it's going to be a struggle. I did summer placements for, I think, 3 years with BBC Transmission Engineering. So I was working at the Daventry transmitting station, which is now closed for one summer, with big radio transmitters that you could actually walk inside. They were so big. Obviously, they had to be switched off when you went inside. So after graduating, I spent a little bit of time thinking nobody's got the right sort of job for me, and I was quite lucky to find a job with a small company that had a big project for them, and they needed somebody else to do some of the work on one of their projects, and they thought they'd take the risk of taking on a new graduate. So for a consultancy company, getting a graduate placement in a small company is quite unusual. Obviously, as a company gets bigger, they're more able to take on people with less experience, but most of the people at this company had many years' experience. It's a company that specializes in solving problems for other companies. That's effectively what a consultancy means, and they specialize in radio work, which is quite a niche. So they would work on building prototypes and proof of concepts for companies before they got funding and took that to like a bigger design team. Or sometimes people would come along when they already had the prototypes and they didn't quite work, and it was just a little bit too hard for them to get them to work. So it was very varied work. Some of the projects would be just a week or so. Some of them would be a few months. Most of the stuff that they didn't last for kind of the whole cycle of the design from concept to production, but sometimes it did. One of the projects that I worked on involved building hundreds of prototypes for a field trial. So I spent my weekends in a factory. It was the only time that we could get use of the factory was at the weekend, because they were building other kind of real product during the week. So we built hundreds of prototypes. We had to work through getting them all tested. So I saw that if you build 100 prototypes, maybe 50 of them will work, maybe 80 will work, but you'll never get them all to work. So some of the work was about trying to optimize the design so that when you build 100, you get a little bit more of them working and you don't have to modify too many of them. So this was quite interesting and very real work. So that kept me busy for the first 5 years of my career. And then I went to work for a relatively small company that spun out from the university with a kind of a new technology concept. So they'd got some venture capital funding. They had plenty of money. They had recruited a load of people to do some work, and they'd got an interesting idea that they were trying to turn into real product that they could sell to people in other countries in large volumes. So we were planning to build tens and hundreds of thousands of units. And the idea that they were working on was a wireless last mile for broadband. So in the UK, everybody still pretty much gets their broadband over the phone line. It used to be limited to 64 kilobit, maybe 128 kilobit if you got a really fancy dial-up at the time. And the concept that they had was to do a short link by radio, which could generate quite a lot more bandwidth. And if you shared that between lots of users, then it would be kind of cost effective. So you'd still need a high capacity link at the other end, which would be probably optic fiber even at that time. So now we've got to the point where people have optic fiber coming into their own houses, and quite a lot more than 25 megabit to everybody's house. But if you think about countries where they don't have phone lines already installed to every house, and they were starting to roll out internet and broadband, then this seemed like quite an interesting concept, hence getting some venture capital funding for it. And it was similar to the type of design that I was working on for the first project that I started with the consultancy company. So I'd got some pretty specific knowledge about the type of product that they were building and how it needed to work. So when I started with them, they had prototypes that were working, and the task was really to take that into mass production and build it in large volumes at a fairly aggressive cost. I don't remember the exact costs, but they were probably trying to reduce the cost by maybe 5 or 10 times from the kind of one-off builds that they were doing. I stayed there for 9 months. The product was, I think, struggling to be commercially successful across the market in comparison to the other opportunities. The technology did carry on. There was a spin-out company that kind of took over what was left after I left, and they have only just gone into administration. So they have been successful up until now over the last 20 years, but they don't seem to have finally made a real product. Partly because I think the mobile technology has overtaken them. So the technology that everybody has in their mobile phones, even in developing countries, that has replaced this more specific technology. And when you get a general technology that replaces something specific, it often turns out to be cheaper. So at that point, I kind of felt that I needed to make a change from that company, because to me, it didn't seem to be going anywhere. And I started looking around for other things that I could do. So I'd been working on analog design and specifically radio frequency design. And that I think is still seen as a bit of a black art, because you have to kind of guess how a circuit is going to work in a sense. It's very difficult to model it accurately, not just because the models are complex, because you don't understand from just looking at a circuit what you put in your model to represent the actual circuit. So you have pieces of wire that aren't really just connectors anymore. They're inductors and they're capacitors, and they have resonance. So just a short piece of wire can be represented in a model as several different components all at once. And if you don't understand how to model it, it gets very confusing. And at the same time, back then, digital design was also quite rare and specialized. So you could buy programmable logic devices to do small fixed function type features, but they were very small. So they would have maybe 32 elements or 64 elements in them that you could program, and they weren't used for anything very complicated. And people were obviously building ASIC silicon chips, but that was a very, very specialized field. So at the time I was in school, people were still doing digital design in kind of tape layout. So you would draw your digital circuit as a collection of physical gates. Now we use a language to represent the type of function that we want, and then we use computer software to translate that into the physical layout. So we don't anymore get involved with what the what does a gate look like is done by one team, and then that's just reused many times by people designing the circuit. So we design the circuit, but we use a different type of programming language, where rather than executing every line in a sequence, as you would in a normal piece of software, all the lines get executed all at once. So it's a completely different way of looking at design. But ARM was the obvious kind of, if I'm going to change career at this point, then ARM is somebody that I should look to. And they were obviously doing digital design. I had a bit of a challenge with the interview, because they asked me kind of a standard set question that you would see maybe even in A-level electronic design, and I hadn't even seen that question. So how would you build an adder was something that I understood the question, I knew how to answer the question, but I'd never actually seen it as, well, this is the answer to this question, because everybody will ask you this question. So I went into the interview not knowing quite what to expect, and I got a bit of a shock there. But I think I had the experience to be able to answer the question from first principles, which was enough, even if I couldn't answer it properly. And I had a good software background. I'd been using computers since I was maybe about 10, when the first cheap home computers came out. So I'd done lots of software, and software is a very important aspect of testing a computer. You write software to run on the computer to check that it can do the right thing. So I made the switch from analog to digital. So at this point, it's maybe worth checking if there's any questions about the analog side of it before I move on to the digital side. Right. So I guess quite a lot of people have heard of ARM by now. Certainly living in Cambridge, it was the only tech company that you could assume that people might have heard about. And it's getting a bigger company, so it's getting a little bit more visibility. So the way that the company, or any company, makes money is what we term a business model, and different companies have different ways of making money. So the core business for ARM is designing processors. We design 1 or 2 processors every year on average, and this is 50-year-old technology. Even before the home computers of the 70s and 80s, there were computers being built in roughly the same way as we build them today. Not in terms of the process that we go through, but the functionality of the computer hasn't changed massively in 50 years. The features that we bring are security, energy efficiency, and we also design computers that can be used everywhere. So not the same computer, but different computers will fit into lots of different potential slots. The company started out as a small team working on a very specific design, and once they'd got far enough along with that design, they had the opportunity to turn their initial work into a commercial product, which they could license to lots of other companies. So the idea is that if you do some work once and it's sufficiently generic, you can sell that many times to lots of different people, and they can all use it in their designs. So it doesn't just apply to ARM. This is quite a common way of making money. It's cheaper for one company to do the work and to sell it maybe 10 times at maybe an eighth of the price. So everybody profits by doing that. Everybody pays some money towards the cost, but not necessarily as much as they'd pay if they were doing it all themselves. And on top of the licensing, we charge a royalty. So for every device that somebody makes, they give us a small fraction of the cost of that device. So this takes a long time to get started. It may take 3 or 4 years before a company starts to ship in any volume. But once they've started to make things, that potentially carries on for 10 or 15 years with maybe the same product. So we sell them the rights to use the design for a fixed amount. And then as they keep on making that over the next however many years, they keep paying us a little bit of money all the time. One of the other things that we do that's quite successful is we standardize a lot of the work involved with computing, so a lot of companies can work together. So we have standards for the instruction set. We have standards for the physical interfaces for how things connect to each other on the chip. So we enable software, and we enable other people to do hardware designs that can interact with what we do. So there's tooling, operating systems, different components all come together from all over the world to help people to build products using our design, using other people's designs as well. And generally that's a lot more efficient than one company trying to do everything all on their own. And it's been successful. We've grown from about 200 people when I joined in 2000 to about 7,000 worldwide today. And of that 7,000, about 3,000 are in Cambridge. So that's quite a big employer. And it's not just Cambridge. In the UK, we've got offices in Manchester. We've got a few small offices close to Manchester. I can't remember exactly how many we have in the UK. It's maybe 3 or 4 design offices in the UK. We've got design offices in France and America, and we've got small offices pretty much all over the world. So the main thing that we sell is what we call intellectual property. So we don't sell very much that is kind of physical that you could buy in a shop. We sell a design. We sell designs for not just the processors, but for graphics, for the interconnect to connect the different parts of a computer together. And we sell subsystems for, we kind of put things together in a standard way that almost everybody would find that a suitable way of putting them together. And then other people can add on their pieces around the outside. So this saves them doing a lot of the less interesting part of the work. It gives them the opportunity to quickly make something that's unique without doing all of the work. So they pay us for that. But again, because we've got the experience of doing it, it's cheaper for us to do it than it is for them to do it. Customers add their own unique ideas, and they will also buy designs from other companies. So they will build something to solve a specific problem. It may be a generic device. It may be a specific market that they want to build. So if they're building a product, they might want to build something that fits exactly to do just the work that they need. So if you think about building kind of an MP3 player, I know not many people have a standalone MP3 player anymore now that you can use your phone to do it, but you might have an MP3 player actually built into the phone so that you can play music with the screen off without using very much battery power. But you might put all the parts that you need in that specifically to play just music. So you might have the ability to read data off the SD card, to decompress it, to turn it into audio. You might have some filtering, you might have some specific acceleration, all designed to just be capable of doing that and no more. So because it's targeted, it's more efficient, so you get better battery life. Or you might make a very generic design that has a few more features than anybody needs, but it would be a suitable device for hundreds of different companies to put into a low volume product. So, and the difference depends, are you building 10 of this device or 100 or 5 million of them? If you're building millions, then it makes sense to do your own design. If you're only building a few hundred, then it's not cost effective to try and do your own design. You have to use a standard part. And this wide range of different opportunities is one of the reasons that it's effective for us to do a design and sell it to lots of different people, because different people have different applications. So I don't do anything with robots, but a lot of the applications, robots is a kind of a very big part of what's coming along today. I might mention that a little bit more coming along. So the silicon part of the design that we're involved in, it's a tiny part of a final product. If you think about what you'd go into a shop to buy, that will have maybe a screen, probably a battery. It'll have a plastic casework. That's a huge part of the design process that is nothing to do with what I work on, but it's still a big part of the product. The packaging for the product. So this is kind of a different sort of design. The design for the packaging, the kind of the branding on the packaging, it's all design, but it's not what I call design. Any typical engineering job fits somewhere between the designing the IP, which is what I'm doing, somewhere along between there and designing what somebody would actually buy in a shop. You wouldn't normally see any company doing the whole kind of end-to-end process. You'd span, in a typical company, you'd span a very small part of that sequence, but it maybe gives you an idea about how many different potential career roles there are. And in ARM, the pure designing things for their own sake might be about a quarter of the jobs out of that 7,000 people. A lot of it is still technical, but a lot of it is somewhere between designing something that's going to be reused and helping other people to do that design. So to come on to the end products, a lot of the early success of the company was around mobile phones and MP3 players. In the days when people did have a standalone MP3 player, and tablets, cameras have processors in them. I guess it's a little bit more obvious now that the cameras have a lot more features, and you can see that they're doing processing as they're running. TV boxes, smart TVs. So a lot of this stuff is not very exciting. It's all kind of mundane infrastructure. But if you think about how many of these devices you might have in your home, potentially there's tens or hundreds of these devices in the house. So even if we only make a couple of pence out of each one, it adds up over the whole world. There's a lot of small battery-powered devices that are more popular now than they were 10 years or so ago. So fitness trackers is a good example of something that doesn't have a screen. That's probably a bit of a unique thing that wouldn't have happened a few years ago. Bluetooth headphones, all the smart lighting. So every light bulb now potentially has some sort of radio interface in it and some sort of computer in it. And if you're going to avoid other people controlling your smart lighting, then it needs to be secure. So this is kind of how things all come together to make it more challenging now than it was 5 years or so ago. So you could get smart lighting 5 years ago, but it wasn't, nobody was worried about it being secure. Now, companies are a lot more concerned that their smart lighting products are difficult for other people to interfere with. So we have to continually upgrade the products that we're designing. Lots of computer peripherals, hard drives, Wi-Fi, routers, even the keyboard that I've got here has a small computer inside it because it's a reprogrammable keyboard and it's got backlighting and lots of fancy features. Lots of very small computers everywhere. Automotive has been a field that we've been involved in for a long time, initially with things like anti-lock braking, where you've got a small computer looking at, are all the wheels turning at the same speed? Has one wheel locked up? And if so, how do you adjust the braking to stop the car skidding? So that's a very kind of well understood piece of automotive safety. And it used to be 10 years ago that most cars didn't always come with that as a standard. Now it's every car has that. It's pretty much standard everywhere. The new thing that not all cars have is self-driving. So a few cars are getting close to being able to self-drive some of the time. A lot of companies are interested in making cars able to drive themselves all the time for a variety of different reasons. But it's an area that is seeing a lot of research at the moment. And I think the safety and autonomy is really one of the areas that I would put robotics into. So you have lots of robots in factories building things. They have to be safe because they've got potentially very big, powerful motors in them. If they go wrong, get confused, forget where they are, they can cause a lot of damage. Even if there's nobody in the factory, they can. You need to make sure that your factory never kind of destroys itself. You need your robots to be able to tell what they're looking at. If it's doing some manipulation on a production line, you need it to be able to have good enough vision to be able to detect if the things that it's picking up are what it expects, if something's fallen over, if it needs to stop and get help from a real person, that sort of thing. So a lot of these technology aspects cover quite a wide spread of different applications. So we have robots now that can walk around outside and do simple tasks. It's not really any different from a car driving itself. In a way, a car is quite a simple robot to control because it's only got two controls, like forward and backward, and how much do you turn the steering wheel? So a car is a very simple robot to control. If you think about the robots with legs, where they can walk and they can balance, or a drone where it's got 4 propellers and it uses the propellers to control the direction that it's pointing in, those get a little bit more complicated. And to control something like that, you have to be making adjustments to what it's doing 100 times a second, maybe a bit faster. So you need a computer that can do lots of calculations fairly quickly, maybe with fairly good control over exactly what it's doing. And that's quite a different challenge to building a computer that can do lots of work very quickly. So the other area that we're starting to move into is what we call cloud compute, where we have or somebody has big racks of computers, and if somebody needs some work done, like a video conferencing feature. So 3 months ago, there was a massive demand for video conferencing capability. And all the companies that were providing it, they didn't necessarily go out and buy more computers themselves. They rented that computing ability from other people that were dedicating just racks and racks of computers to, if anybody wants to buy this and use this computer for half an hour, then this is what we charge. It's getting more common to rent computers from a third party than it is to own your own computers. If you need a lot of compute and you don't know what it's going to be tomorrow, it's cheaper to rent it. But this is one area where efficiency is important. If you've got thousands of computers, they all need to be kept cool. The more efficient they are, the easier it is to keep them cool. And last month, the newest powerful supercomputer came online, and that was the first big ARM-powered supercomputer that has 7.3 million cores in it. So they put 28 cores in each chip, which is not a new idea in itself, but it's a way of getting them closer together so they can talk to each other more quickly. And this thing consumes 29 megawatts of electrical power, which all turns into heat. So if you're thinking about the efficiency of a computer doesn't do any kind of mechanical work. Everything it consumes turns into heat. So energy is always an important thing for computers. The more power you use, the more cooling you need. So in a mobile phone, the whole thing is limited to typically about 5 watts, because that's as much as you can put into a palm-sized piece of metal or plastic and have it dissipate that into the air without getting too hot to touch. So does anyone want to ask any questions about kind of the business and what products we work on? So to come back to the question of what do I work on, I don't work on any of these. All I work on is making these things possible. So I'm working on kind of the engine for the design, and at the moment other people are taking those designs and building them into whatever they think customers will want to buy. So if we go back to 2003, which is when I moved into CPU design from system design, which is where I started, the company employed about 250 people, and at that point there were 19 offices. a little bit easier to count than it is now. The main design offices that we had at that time were Cambridge, Sheffield, where we still have an office, Austin in Texas, and Nice in the south of France, where I spent 6 months working. 2006, I spent a 6-month secondment in Nice. Our partners at that point had shipped 282 million processors, which that's one for every, I don't know, 100 people, I think. So not a huge number, but still a good number. And the processors that we were designing at that point were Cortex-M3, a microprocessor, 968, which was used in mid-range phones. So if you'd bought a phone in 2003, or if your parents had bought a phone in 2003, it would have had probably a 50% chance of having a 968 in it. And the kind of the high-end processor that we were building at that time was the 1176. So at that point, 350 people, we had three kind of main designs that we were working on. And that 1176, 8 years later or so, that went into the first Raspberry Pi. So that went from a high-end product to what's the cheapest thing that we can build a $25 computer around. So that's an example of the long tail of the royalties. So people weren't using 1176 in phones anymore by 2011, but they were still using it in kind of computers that went into production lines, small factory type products. So factory robots in 2011 would have been using maybe 1176. So it moved from being a high-end phone processor to a good processor, but very cheap for a much smaller target market. 2003, we had just announced the AMBER AXI bus protocol for connecting things on chip. So if you want to connect your processor to your memory on chip, AXI would have been the way to start thinking about doing it at that point. We had just announced what we call Trust Zone, which is an on-chip security mechanism, a way of telling the hardware what the software should be able to do and what it shouldn't be able to do. And we've just announced CoreSight multi-core debug and trace. So this is a way of working out what's happening when you've got several computers all built inside one product from the outside. Debug and trace is the area that I work in, and it only becomes important when you get to the point of, my software doesn't work, I don't understand why not. So you need to see exactly what's going on the inside. At that time, Nokia and Symbian OS were the dominant types of phone. And I wouldn't be surprised if a lot of people here haven't even heard of Nokia and Symbian OS. They've been replaced by newer things. This was 4 years before the first smartphone, so the Android, iPhone type devices. And the newest design, which is the one that I started working on, which is still in use today, is the Cortex-M3. So this is a microprocessor. It's usually built as a standalone chip that will run code on its own. It doesn't need any support hardware necessarily. Most of the company was designing processors for phones and various applications. Phones still couldn't do very much more than just make a phone call. There were limited internet connections on a phone, so you could do email on a phone. You could just about connect to a website, and that high-end processor would just about run the first generation Raspberry Pi. If you've used one of those recently, they're really quite, and they work, but they're quite slow as a general purpose computer. But the target there was very much price driven, and that high-end device at the end of its lifespan met that price point. So the Cortex-M3 design was a new concept for ARM. We were trying to get into the area of low performance computing. So things like dishwashers, things like microwaves, where you want some compute capability, but you don't need very much. It's a massive market, very, very cost sensitive. Nobody makes very significant profits on what they sell, but they sell a lot of them, so they do make some money. And at the time, all the designs were 8-bit processors. So the derivative of the first computers that I started to program on 25 years previous to it. So what we did is we looked at what does this design need in this target? What does it need to do? So we thought about a new architecture, which is the kind of the high-level view of how does the computer do what it does. So we looked at in the performance of what you're doing. So if you think about something like maybe today a drone, it needs to be able to react very quickly to events. It needs to be quite deterministic. So you need to know if you start doing something and then you have to switch to doing something else, that you can do that. So we built a few things into the architecture to make it what we thought was a good target. And everything else we built as small as possible. So we didn't add anything that we thought was unnecessary. So think about the architecture, it's kind of a difficult concept. If you haven't built a computer before, you don't really understand what the architecture is. But if you think about all the different types of cars that you've got, if you look at any one car, you'll see lots of other cars that are similar. But if you look at all the cars, you'll see some are petrol, some are diesel, some are electric. So there's a choice of engine. They've got 2-wheel drive or 4-wheel drive. And it's quite an obvious choice. And depending on what you want to use the car for, you might pick one or the other. You might have a 2-seater car. You might have an SUV type car. And so the computer architecture kind of fits around this sort of choice. So everybody knows what a car looks like. Everybody that's designing computers knows what a computer looks like, but there are many very different types of computers. So we tried to design something new that would address a new market in a good way. So we tried to make something optimal. And this design took, I think, about 10 people to do the design. And it seems that we spent roughly 2 years. So a couple of years ago, I went back to look at this design. It looks like from when we started the work to when we had a final product, it took us about 2 years. So it's a relatively small team. So coming up to today, when the most recent designs that follow on from that were built that you could actually buy, we've got a lot of different applications that didn't exist 15 years ago. So this is one of the things that I think is very important when you look at what are you going to be doing as a career. If you think about the scope of what you can do today, that will be it will give you the wrong view of what things are going to be like in 10 years or in 15 years' time. If you think about the stuff that we have now that didn't exist 15 years ago, the drones, 3D printers, VR headsets, none of this was common 15 years ago. That one design has now spun out into 8 different designs to cover a much wider range of performance. So what we thought was small, 2 or 3 years later, we managed to halve the size of that design, because having built it once, we understood better where we could make it better, and we made it smaller and kind of faster, but not so powerful. And we've got another 2 designs that we've announced that aren't yet available. So this one line of products carries on growing. Now it's a 17th the size. It's faster and it's more power efficient. And the power efficiency gain means that you can run it off a smaller battery. The fact that it's smaller means you can put it into a pill that you can swallow. So you can now get little computers embedded in pills that can take readings as they go through your body. And the design from 2003, you can actually download that for free evaluation now. You don't even have to be a proper company. Everybody can download that if you've got the right tools and you can play with it. And that was one of the small projects that I worked on, was to package that up. So one of the questions about learning pathways to get into ARM. So we typically take people post-university. There are a fairly small number of universities that do computer design courses that would lead into directly the sort of work that I'm doing. Obviously, we have a lot of software work as well, which allows a little bit of a wider background. And then for the less technical roles, we've got potentially opportunities for people with a less specific technical background. But we recruit, I don't know, 30 or 40 graduates every year, and maybe a few people with a lower level of qualification. So we are trying to expand. As the company gets bigger, it's easier for us to take a wider range of people, but we're predominantly looking at graduate entry. But that's just for one company. If you're looking for different types of engineering or different positions in an engineering company, then there are other opportunities as well. So running out of time, because it's hard doing this when you're just talking to yourself. So the design I'm working on, I've been doing this for since 2003, effectively. This is the 9th iteration of what I'm doing. Every time it gets a little bit harder because it's working with a more powerful computer on the other side of it. But I'm fitting into interfacing into the computer to give people visibility of what the software is doing. So I did say that I would talk about design and test I think this is one of the areas where there's a wider scope for different levels of qualification, because the design side has a lot of very specific knowledge. The testing side is a little bit less specific. And to some extent, if you don't understand how it's working, you might make different assumptions about what might confuse it. So we're talking about trying to make sure that the design doesn't just work some of the time; it works all the time, irrespective of what you do with it. So we spend a lot of time trying to test designs. More than half the project will be checking that the design really works properly all the time. We don't just do CPU work, we do quite a lot of graphics work. We're doing some work on enabling artificial intelligence, so the hardware to make artificial intelligence faster. We do lots of software work, so a lot of it is based around Linux and open source software. This comes back to the big ecosystem of different lots of different users all using the same big group of software. We do a lot of FPGA modeling, which is a way of building a model of a computer or a specific design cheaper than putting it into silicon. So there's a lot of FPGA work in computer engineering. A lot of people will make products with FPGAs, but it's a completely standalone field from where I work. So I work with people that do that, and it's a whole area in itself. We do software modeling of the computers for performance and testing software before it's finished. Tools to work with the hardware. And if you're non-technical, or if you start technical and you decide that you'd rather be less technical, or you know that you're not technical and you're interested in computing, there's a huge area of customers or documentation or sales and marketing, legal. So IP has a lot of legal. We have to have contracts and things, and project management is another massive area that's very critical to us. So I have just fit in everything that I wanted. I don't think I've missed too many questions. Right. See if I can stop. So yeah, any questions? Send them might be an email.